The distal convoluted tubule and the collecting duct are the last part we're going to talk about here. So here's the distal convoluted tubule and the collecting duct, and the collecting duct of course would be joining other collecting ducts coming in with urine at the end. We've come up from the ascending loop of Henle, and in the collecting duct I said something that wasn't quite accurate before. I said you have a high concentration of wastes, which is true. What you have is about 60 milliosmoles here, which is much lower than the 300 milliosmoles outside. But nearly all of what's on the inside here is wastes plus just a little bit, few valuable molecules. Enough to make it worth recovering them. And so that's what's happening in the distal convoluted tubule. So what we have again are some secondary active transporters that again use sodium to recover glucose and also sodium amino acids, a little bit of calcium. So there's some valuable molecules that are still being taken out here. There are some wastes that are being added through several mechanisms. So some specific kinds of waste molecules are actually added at this stage. So by the time you get here, you've got urine. It's in the neighborhood of 60 or so milliosmoles, differs for different species some. And at this point, it could just be excreted. Let's say that an animal has excess water. You or some animal's been drinking more water than needed. In that case, water is also a waste product and simply winds up being excreted. Okay, and you'd have all of those wastes along with the excess water. The alternative is that an animal is a little bit dehydrated, and if it's dehydrated, then it produces ADH, the hormone ADH, which is the same thing as vasopressin. And ADH binds to cells that are in this epithelial layer of the collecting duct, and it causes aquaporins to be put into the membrane. So this is happening only if ADH is secreted. In that case, as this urine is moving down, it's going to start encountering extracellular fluid that's at higher and higher concentrations. And the result, of course, is going to be that water moves out. So if there's no ADH, then we get rid of dilute urine, but it still has all of the wastes in it. Remember, the entire number of wastes, every single one of them that was here is still in it, but you're also getting rid of water. If there's ADH, contrast, then in that case you might get rid of urine that could be around 1,000 or a little higher milliosmoles because you've recovered most of the water from it, but it's exactly the same number of waste molecules. So if we put all this together, what we've had is a system up above here where we developed a filtrate, recovered valuable molecules in water, recovered more water as the water left to dilute the blood coming from the area of the medulla that's high in solute concentrations. We moved sodium and chloride out of the ascending loop of Henle, and it moved into the blood, carried down deep into the kidney. That left behind waste molecules, but still with some valuable molecules in the distal convoluted tubule. In the distal convoluted tubule, we recovered some remaining valuable molecules, added a few more wastes, wound up with urine that's in the neighborhood of 60 to maybe 100 milliosmoles. At that point, we can excrete it with the extra water. In that case, we get rid of excess water. Or if there's ADH present, then aquaporins get put in there, and the high solute concentrations outside the collecting duct wind up allowing water to move out through the aquaporins, and you produce much more concentrated urine. In either case, it's about the same number of waste molecules.